Okay, so what we're going to be transitioning between this time around is we're going to go from the motion of a particle, where it's just simple translational or curvilinear motion, to the motion of some kind of a rigid body. And the big difference is, for a rigid body, if this thing is rotating, different parts of it are going to have different velocities. So if you consider what's the velocity at one side of this tennis racket versus what's the velocity at the other side. So even though it's one chunk and one piece, different parts of it have different velocities. And that's the main difference between a rigid body, which is like this tennis racket, versus a particle, which would be like this little racquetball going along. Okay, what we're going to do for this, so yeah, here's another demo that if you think about what's the velocity of that racquetball up there versus what's the velocity of the handle, they're going in different directions, right? So maybe the entire thing is moving together, but as soon as you introduce rotational motion, that's where the velocities of one part of this are going to be different than the velocities of the other part of this. What we're going to do to segue into the motion of rigid bodies is we're going to break that rigid body up into a bunch of different particles. Okay, so you can think of the thing is made up of atoms. And every little atom on here, if it's rotating, is going to have a different velocity. Okay, so if you think of the rigid body as a collection of particles, a group of particles, that's going to be the point of this chapter. We're going to look at systems of particles. And if you understand the motion of a bunch of systems of particles, this is going to segue into later connecting all those particles together to analyzing the motion of rigid bodies. And hopefully this is not overcomplicating that. Okay, I'm going to go ahead and steal this little video that MIT did. They've got a tennis racket and a spoon or something, a couple different objects, and you see these rigid bodies, these large objects, as they're thrown, they're flopping around all over the place. But something magical happens when you paint the center of mass with glow-in-the-dark paint, and then now we're just looking at the center of mass. And you can see the center of mass follows a nice, beautiful, parabolic trajectory. It's not flopping around. It's not confusing. So even though the entire object is flopping around and different corners of it have crazy velocities going on, the center of mass is doing this very simple trajectory motion. So this is, chapter 11 stuff, chapter 12 stuff. So if we can take that big, ugly, complicated rigid body system and change it to just looking at the center of mass, this is going to make life so much easier. And this is also going from systems of particles, okay? So the entire system, and these guys, right, consider it that it's made up of a bunch of different atoms or something, right? So as you're flopping that tennis racket around, and each piece of it has crazy velocities and it's doing crazy different things, and it looks totally complicated. But if we group these all into just one group of particles and we figure out what the center of mass of the thing is doing, that's going to make life livable. Okay, so the name of the game is we're going to add everything together, figure out what the center is doing first, and then when we figure out what the center of mass is doing, then we can take the next step and say, okay, how is it rotating around the center? And the overall motion of each individual piece of it is going to be a combination of what the center is doing and what that edge is doing relative to the center. So hopefully that'll make a little bit more sense of the point of systems of particles and looking at the center of mass of those systems of particles. So just watch this MIT video a couple of times and be happy that the center of mass follows these nice, normal trajectories, because that's the game of engineering, is how can we simplify complex systems. Okay, so here we are with a PhET simulation. I'm going to go over to advanced, which allows us to have 2D motion you can add more particles. So we are creating a system of particles here. And the cool thing about this, we can turn off and on the reflecting borders, and we can also mark the center of mass. X marks the spot over here. So what I'm going to do is I'm going to set these guys up to have some kind of an initial velocity, and we're going to watch just the chaos that ensues. Okay, so all these velocities are going to be going every which way. I'm going to set this to try and have quite a few collisions happening here. Okay, so they're all going to kind of be aiming over here towards one another. And you can set the masses of these guys over here, or if you hit more data, you can actually type in numbers. So instead of just like randomly grabbing these guys and moving them around, you can also come into this table and give it Vx, Vy velocity, set the exact starting position. So this is a great little simulation. This is similar to what a molecular dynamics simulation is, or discrete element modeling, where you have discrete particles and it's going to have little time steps. Okay, so we have this scenario set up. We're going to play it. Let's see. Oh, we have elasticity too, so we can play around with like the coefficient of restitution. Yeah, let's leave that all the way elastic in here. So here we go. We're going to play this thing, and they collide, and it's chaos, and everybody has different velocities. Okay, we can go back to the beginning and restart it. So let me turn down the simulation speed, see if that we can see it better. Yeah, so everything is going kind of chaotically, and you say, how are we supposed to keep track of this chaos? And in systems of particles, and again, this goes back to like chemical engineering and PV equals nRT, the ideal gas law, that's the little, molecules that are bouncing around in the air right now. Do you usually have to keep track of the velocity of every single little atom? Like if you're going to measure the temperature of the room, is it going to be the temperature of the just one atom? Or you look at the average overall picture, right? And that's what we're going to do for this guy too. So instead of keeping track of all of the different individual particles, we're going to turn on the center of mass marker. And what I want you to do is keep your eye on the X. Ignore what the particles are doing and just look at X. And I want you to ask yourself the question, as these collisions happen, as the particles bounce around and do all this random stuff, is what the center of mass doing random? Okay, so the center of mass, hopefully you'll be able to see that it is not random, that it has a constant motion. We're talking, x equals x naught plus vt kind of motion, just constant acceleration type motion. Okay, so here we go. So watch the X. Keep your finger on it. If you put your finger on the screen and just trace the motion of X with your screen. And again, ignore what the particles are doing and just watch the center of mass. So did you see it? Even though the particles are going in crazy directions and crazy different velocities, the center of mass has a constant velocity and a constant direction. It is moving with a nice, simple motion, just like the tennis racket from the MIT demo, okay? So everything around it is chaos, but if you add together the average of the entire system, is very simple motion. It looks like a single particle moving. Okay, now in this case, I turned off the reflecting borders, and I did that because this will introduce external forces into the system. Okay, so internal forces would be between the particles, equal and opposite. So 4 bumps into 2 and 2 bumps into 4, and if you add both of those together, they cancel each other out. If one of these particles hits the wall, this is external to what all the particles are doing, and that external force will change what the center of mass is doing. So let's try this one more time, and this time we have the reflecting border on here, and we can start it with some velocities, and it's constant, constant, constant. Did you see what happened to the center of mass as soon as these reflecting walls are hit? Now it's changing direction and it's changing. So external forces are going to mess around with what that center of mass does. Internal forces won't do a thing. So we're going to just group all the particles together like they're one object. We'll worry about external forces. So if wind is blowing on everything, if there's a wall that's going to change the direction, something that is not a particle that's acting on it, that's going to change what the center of mass is doing. But the internal forces between particles, we're not going to worry about that because they cancel out with one another.